Hey guys, welcome to the fourth lesson on data structures using C++. Today we're going to be talking about array-based stacks. We're going to talk about, again, the concepts of having an array-based data structure, like we did in the first or second lesson when we did the array-based list. And then we're going to talk about what is a stack, what makes up a stack, and yeah. All right. So basically, a stack is just a data structure or a specific data structure that follows this specific rule, right? So a stack is like any other data structure. Like we had an array-based list. We have an array-based stack. We can have a linked list-based stack, like we had a linked list. And a stack is, like I said, just follows this one rule. And the rule is that the stack has to be last in, first out, or LIFO. It just has to follow this idea of last in, first out. And what that means, last in, first out, is the last item that is added into this data structure or added into this collection will be the first one that's taken out of the collection. And a good way to visualize this is a stack of something. So let's say we had a stack of books. Let's say we have a chemistry book. We place the chemistry book down on a table. We then take an English book and then place it on top of that. We take a C++ book, we place it on top of that. So now we have three books in this stack. The first one, which is chemistry, is on the bottom, and the last one, C++, is on the top. So the last one that we added to the stack was the C++ book. That was the last one. So the first one that we take out is that one, is the last one. So if we were going to take something off that stack, it would have been the C++. So in order, if I did chemistry, English, C++, now I want to empty the stack, I would take off C++, English, chemistry. It goes in that order. And you could think of, a stack of dishes, a stack of trays, a stack of books, anything that you have a stack. Now, this is just some terminology. When we add things to a stack, we call it pushing. We push something to a stack. So we push something onto a stack, and now that gets added to the stack. To take something off of a stack, we pop it off the stack. So if we pop something, it takes it off the stack. Or takes the last element off the stack, because it's last in is the first one out. Now, we come back to this idea again of this abstract data type that we talked about in the last lessons. And how basically what that means is that, all the user has to know, when they're using this data structure that we build, is that really only the thing they have to know is that it's a stack. And how it's implemented behind the scenes is really up to the programmer. We're doing an array-based version of it, but if I did a linked list version of it or a linked version of it, the implementation details behind the scenes are really completely up to us. But the overall idea of having a stack, that has to stay universal. I mean, we have to have these push and pop. Well, we don't have to, but we should have these push and pop functions and have some other generic functions that all users that are used to stacks should have. And that I could take this definition of my stack and, switch the implementation behind the scenes, and the user wouldn't know. He would still interact with the public interface of this stack. And even though we changed behind the scenes, they really wouldn't be affected. If you come from languages, even with C++, they have built-in data structures for you that you can use, and you just kind of use them, right? And in the standard, in the STL, they have some data structure that you can use, and you'll just create them, add items to it, remove items to it, and you'll just use that to manage your data. And you don't really care about how they're implemented. Essentially, you only care about the runtimes that you get on each of them. And you could look up the runtimes for each, normally for functions and things that are included in data structures on websites. Like if you're looking up a C# data structure, you could look on Microsoft's website and you get the runtimes for their functions to see, oh, if you want to use this function or not, to get the best possible runtimes that you can get. And okay, yeah. So now you may be wondering and saying, okay, so this data structure called a stack has this motto: last in, first out, or LIFO. And you may be saying, why do I want to use a stack? Why don't I just always use a list? Or why don't I always use a queue, which we haven't talked about yet? But why do we want to use a stack? And the reason why we want to use a stack is because of the idea of last in, first out. By attaching this principle of last in, first out to a stack, you're basically creating this way that you're guaranteeing certain runtimes on certain functions. Because based off of last in, first out, you can guarantee, your insert and your remove, being big O runtime of 1, or big O1 runtime, or instant time, or constant time, and you can guarantee those things because of how you have to follow this rule of last in, first out. So basically, if you're looking for something that has last in, first out, and you're looking for runtimes that are associated with last in, first out, then, stack might be the way to go. So that's the reason why we have all these different kinds of data structures, because, like I said in my other video, knowing all these different types of data structures are really just separate tools for your toolbox. And when you're presented a problem in the real world and you need to solve it, you need to say, okay, what data structure would be the best data structure to handle this situation? If I need something that has really fast searching speeds, maybe I'll use a binary search tree. Or, if I need something that has last in, first out, I'll use a stack. And then even on top of that, then you have to worry about, okay, do I want an array-based or linked-based, and for stacks and queues and lists. So that's what data structures is really all about, like I said in other lessons. So with that all aside, let's go ahead and build a stack. So like I said, we're going to be doing an array-based stack, meaning that we have a data structure called a stack that has the last in, first out motto, and the implementation behind the scenes will be using an array. So off the top of your head, you instantly know that if we have an array, our push function to add things to our stack can get a little bit messed up and a little bit tricky if we add a lot of items, right? So if we set up our array to, let's say, hold 100 items to start out with, if we get past those 100 items using an array base, we have to implement something that will make it grow and get bigger, which requires a big O of n runtime, because we have to copy everything over to the new array and do all that kind of stuff. So whenever you see an array-based implementation of anything, if you are going to be adding lots of items into this, you are going to have some problems down the road, and maybe a linked version will be a better way. However, for this example, we're not going to be worrying about having to resize our an array and stuff like that. If we are, if our stack is full, we won't do anything. Instead of resizing it, maybe in a more advanced stack implementation video, we can do some resizing and stuff like that. Okay, so let's go ahead and start building our stack. So let's go ahead and create our class. And we're going to just call it stack, just to make it simple. So some of the members that we're going to open up for the public, or the public interface that we're going to have, is we're going to have an isEmpty function to see if the stack is empty. We're going to have an isFull to see if it's full. We're going to have an initialize stack, which will be used to just kind of reset it. We'll have a constructor. We'll have a copy constructor. We'll have a function to see the top of the stack, so what values at the top of it. We'll have a push, a pop, and a destructor. That's it. And then for our private members, we'll have a couple other things that I'll talk about here in a second. So let's go ahead and build the public interface. So like I said, the first function is going to be is empty stack. This is going to be to check if our stack is empty, and we'll just mark it with const. I'm assuming everyone knows the basics of C++ before actually going into data structures with C++. So just to recap, marking a function in C++ as const just makes it that that you're just pretty much promising the caller that this function will not modify any member variables of this class. That's what that is saying. So that's our is empty. We're going to have is full stack, and this checks if the stack is full. We'll have our initialized stack, and that will just, like I said, reset it, or set our stack to 0, which we'll see what that means. We'll have our constructor, which takes in a size or how big we want this to be. So if we're creating a stack, we'll say 100 slots because it's an array based. So we'll say 100 slots or whatever. They can pick how big they want it to start off. We don't. This is just implementation details. We don't really have to even do any value. We can just set up. We can say, okay, start with 10. If we add 10, then make it grow to 20, make it grow to 30, etc. We don't really have to ask the user, but this is just for learning purposes. Then we'll have our copy constructor. Other stack. So once again, this is C++. So the reason why we're passing in this stack as a reference is so that it doesn't make a copy. It's passed by reference to save memory. Because we're only really taking the data from this, and we're marking this const to make a promise to the caller that we will not modify this at all. So that's our copy constructor. We'll have a top function that this will just get the value of whatever's in the top of the stack currently. Then we'll have a function to push a new. This will push a new item onto the stack. We'll have a pop that just removes the current top item from the stack. And then we'll have our destructor, and the reason is because we're gonna have our array dynamically allocated. So that's our public interface. This is what our users will have at their disposal to interact with the stack and store data. Now our private members are going to be, we need first our max stack size. This will be used. This will be set when they pass in the size to the constructor, and this will be how big it is. Then we'll have another int for the top of the stack. That will be the top of the stack, so we'll use that to access the top of the stack, and it's an int because we're using an array, and array elements are integer based indexes. And then finally, we'll have our behind-the-scenes array, and this will be our list. This is just a pointer to an integer right now. So that this is our stack class right here. We have our public interface and then our private members that we need. That is that. So now let's go ahead and write the actual implementation for this. So let's go ahead and create. We'll say stack. So first thing we have to include our stack. Okay. So the first function. Actually, let's start with the constructor. So let's go ahead and make our constructor. Passes in an int size. So our constructor is pretty basic. The first thing the constructor is going to do is we're going to set the max stack size. Let me zoom in. We're going to set the max stack size equal to the size that's passed in by the caller. So now that's set. We're going to call initialize stack, and this is just going to set, essentially, initialize stack is only going to set this top to 0. And that's really all you have to do to reset an array-based stack a stack because of what I talked about in my second video, and I'll talk about it again once I go to it. And then the last thing is we need to allocate our array. So we'll say new int max stack size. So that's all our constructor does, and the runtime for this will be big O runtime of 1. This is constant time. So this is pretty straightforward. There's not much to this. Let's go ahead and do the initialize stack so we can see what that does. Initialize stack. And this is all initialize stack does. It sets stack top to equal to 0. And if we think about this, this is all we logically have to do in an array. Like I talked about this a lot in my second video. If we have an array behind the scenes, if our stack top is representing our logical amount of elements in our array, if we set it to 0, to the user, that means that there's no elements in my array, logically. But in reality, there could be, because if we added data before that, there could still be data in our array, but we're saying that there's logically no elements, so essentially that is resetting the stack. And you'll see what I mean by that as we continue. So that's initialize stack. That's all it does. The next, actually, this is big O runtime of 1. Next is empty stack. So this is going to check if the stack is empty. So it returns a bool is empty stack. And all we're going to do is return stack top equal to 0. So basically all this is saying is if stack top is equal to 0, meaning that it's empty. Because notice how we empty the stack, we just set it equal to 0, saying that there's no elements. So we're saying is empty is just checking if it is equal to 0, return true. If it's not, return false. That's what this is saying. Once again, this is big O runtime of 1. Next, we're going to do is full stack. And now this is pretty straightforward too. These are all straightforward, really. Return stack top is equal to max stack size. So what this is saying is if the stack top, which is the top of the stack, so if the top of the stack is equal to the max stack size, which whatever's passed in, that means we're full. We have no more slots left. So return true or false depending on that. This is big O runtime of 1. Okay, let's go ahead and do the copy constructor now. And now this is going to be the first so far that has a big O of n runtime, and the reason is because we're copying. As soon as it says copy, you're probably thinking a loop where you need something to loop over them and copy the data over. And yes, that's correct. So stack and const stack reference other stack. So this is our copy constructor. So the first thing we need to do is, because now the copy constructor, basically, if you don't know what it is this is the constructor for building a class based off of another stack. So you're passing in another stack as a parameter to this constructor of this new stack. So the first thing I'm going to do is we're going to set our max stack size equal to the other stack dot max stack size. So we're getting their max stack size. Then we're going to set our stack top equal to the other stack dot stack top. So now we have their stack top. So that's all set up. And now that we have that, we have to allocate our list equals new int array to the max stack size. So we have to allocate our list to have enough elements for our new max stack size. And this is the copy constructor, so this is why we have to initialize it like we do in our regular constructor. Now that we have that, that's pretty much the basis set up. Now we just have to copy the data over from other stack to this stack. So we'll set up a for loop. So we're saying I is 0, go as long as I is less than stack top, which is the top of the stack. So that's just all the elements that we have, I plus plus. And then set the values of list equal to the other stacks dot list sub I. So this is just a standard copy. This is just taking all the members from the other stacks list and copying them into our stacks list up to the top of the stack. And that's it. This is the copy constructor. We get the values, create a new list, copy the values over, we're good to go. This is a big O of n runtime because we have the loop involved. Okay, so the next function is top. And this just gets the value that's currently at the top of the stack. So the first thing I want to do is I want to make sure that the stack is not empty, because if it's empty, then I'm going to be trying to access an empty element, essentially, or an element that doesn't really exist. So I'm going to do a check. I'm going to say if is empty stack, or if the stack is empty, then I'm just going to return some kind of weird number. And this is just for testing purposes. That's showing that, if you get this number on the top of the stack, it's empty. I mean, we could do other things. We could just display a message saying this is empty. I don't know. We could do lots of things. So that happens if it's empty. If it's not empty, then we're going to return the value of list stack top minus 1. Now, the reason why we're doing this minus 1 is going to be more obvious when we write the push function. But basically, every time we add a member to the stack, we first add it to the current top, so whatever top is. So if it's the first element being added in, top is 0. So we add it in, so slot 0 is holding the top element. Then we increment stack top to go to the 1. So now the 1 has it. So now if we want to get the top, stack top is 1, so list 1 would have nothing in it. So that's what we have to do, stack top minus 1 to get the top. And like I said, when I write the push right now, you'll see what I mean by that. This is also big O of 1 runtime. Let's do the push now. So void stack push constant new item. I don't know why I marked this as const. Let's go ahead and remove that. Not that one. That makes no sense. Okay. So for pushing, all we're going to do is we first have to check for if the stack is not full. Because if it's full, we're not pushing it on. So if it's not full, then list sub stack top equals the new item, and then stack top plus plus. So we add the item that's being pushed onto this stack, or add to this data structure. We add that to the top of the stack, list stack, and then we increment the top to prepare for the next item to be added in. And this is why we have to do this minus 1 over here, because we're preparing for the next item at the end of this. So that's push. Once again, our push has a big O of 1 runtime, which is cool. Pop. Let's do pop, and we're almost done. And then we can test this out. Our pop function is going to check for if it's not empty. So obviously we're taking off the top element. So if it's empty, we're not going to do minus minus. So pop, if it's not empty, minus minus. And this is also a big O runtime of 1. Now, I'm going to explain this real quick. I explained this in my other video. That's why I'm kind of going through this pretty quickly. If we have an array, here, let me open up Paint. Okay, let me fix this. this is always a good way to describe it. If we have an array like this, right? And let's say we have, there's a decent amount of slots in here. And let's say we have our variable. This is our stack top variable, and it's currently at 0. We add an item. Let's say we add 5 to our stack. 5 gets put into the list sub-0, which is this slot right here. This is 0, 1, 2, and so on. So slot 0, we add our item right here. So 5 would go into there. Then we make 0 go up by 1. So now our stack top is 1. So let's add another item. Let's say we add the value 10. 10 goes into the first slot. Then 1 goes to 2. So now stack top is 2. And then we'll add 2. And another item, let's say we add the value 3. 3. And now our stack top goes to 3. So our stack top is 3. And we added 5, 10, and 3 to our stack. So now if we're going to do, what function is it? Pop, which removes the top item, all we do is stack top minus minus. So essentially what happens is our stack top goes from 3 back to 2, and that's it. Even though 3 is still sitting there in memory, it's now essentially gone. Because, look, even though it's still there, let's add another item. What does the code say? It says go to list slot 2 to dump in the item. So let's say we're dumping in 100. So it replaces the 3 with 100 in that slot, and then the 2 goes to the 3 for stack top. And now we're good to go. So by doing pop, all we gotta do is stack minus minus, and that logically removes the element, even though in memory it still could be there. But it doesn't matter, because since we logically removed it, the next time we push something in, it's gonna overwrite what's ever in there. So that fixes that problem. So that's the pop, and then the last thing we need to do is our destructor. And this is just going to delete our dynamic array. Delete. That's all we have to do for that. And then this is also big O of 1 runtime. Okay, so this is the full implementation. This is the stack. This is a pretty basic lesson, to be honest. This is not too advanced. Let's quickly go over each function one more time. So this is our public interface. Let's go over everything we need to do. So our constructor, our regular constructor, takes in an integer, sets our max size. We initialize, so we set the stack top to 0. And then we instantiate or give memory to our list based off of how many elements we want to be in it. Initialize sets the stack to 0, which this is essentially a reset function, because if we had 10 elements and we call initialize stack, we'll now have 0 logical elements there, and we can start adding new elements in, no problem. We have is empty, which checks if it's empty by saying if the stack top is 0, meaning we have no items, it's empty. If it's full, if we have the max stack size. Our copy constructor takes the information needed from the other stack, then it builds our current list based off of the other stack's max size, and then we just do a for loop to copy it over, and that's why we have the big O of n runtime, because we're running a for loop. The top function just checks to see if it's empty, return this value that it just means nothing, or if it's not empty, then we'll return the top of the stack. So list stack top minus 1. So in this example that we actually have, if we called top currently in this, so currently we have 5, 10, 100 in there. If we call top, it goes get access stack top minus 1. So that would be index 2. It would go to 2 and get the 100 and return the 100 in this example. So that gets the top. So top just gets the top value. Push adds a value on top. So if the stack is not full, we'll add the item. We could add, if it is full, if the stack is full. So in an else, if you were like else, we could make, or we could resize the stack and make it bigger so that we can add in more items. If we really wanted to do that, that would be more realistic, because if our stack is full now it just won't add any more items in. I could resize it and then add in a new item if I wanted to do that. That would obviously make my push function big O of n, and that's what I was talking about, where maybe a linked implementation of this could be better. If I don't know, I gotta look at that. It might be better. Our pop function, just if it's not empty, stack top minus minus. Because if it is empty, then we have nothing to minus. It's empty already. There's nothing to pop off of it. And our destructor just releases our memory, our dynamic memory. Pretty basic. So that's that. This is pretty straightforward. This is easier than the linked list example. So let's go ahead and test it out now. So let's go ahead and include our stack. So we'll just statically allocate these. So we'll say stack, first stack, we'll say it has 5 elements, or it has 5 slots available. So first stack dot push, we'll push on a 5. We'll push on a 15, 25, 35, and a 45. So our stack has 5 elements on it. Let's also, for the fun of it, let's push on a 500. Because at this point, it should be full, so this 500 shouldn't be pushed on, so we shouldn't get anything. So if we go C out, first stack dot top, what should this return? Do you think it's going to show 500 or 45? Because if we think about this logically right now, let's open up Paint again. File, new, don't save. With this implementation that we currently have, we have our array that's kind of being built, or our stack. This is our stack. So the first item that got pushed on was 5. So this is what happens with the stack. First item goes on 5, then 15, then 25, 35, and so on. So that's how a stack operates. It gets stacked on top. So our top in this current right here, if we said top, this would return 35 because that's our top element. So the code that we wrote, we're logically, or we're building this kind of picture for people to understand. We're building this picture. And our top of our stack is there. When we pop something off the stack, this gets popped off, so now 25 would be our top. But because we only said that our stack has 5 slots, the 500 shouldn't show, so the top should be 45. So if I run that, we should get, oh, there's an error, of course. Wait, what's there? Oh, okay. I forgot to make it a function. Did I do that on all of these? Wow. I'm a bad programmer, guys. Okay. Let's try that again. And the value we get is 45. So that's the top. So that worked. So let's go ahead and take that off. I don't care about that. So let's try it one more time. Make sure. So our top of our stack is 45. That's correct. Let's go ahead and say first stack dot pop. So that just takes off the first or the top element. So now if I pop that off and run it again, I should see the 35 now. So I should say 45, 35, which it does. It should go down the stack. And if I continue to repeat this, first stack dot pop, and then print, now we should see the 25. 45, 35, 25. And we can continue down all the way to the bottom. Except let's go ahead and try some stuff. Let's go ahead and do first stack dot initialize stack, and then display the top. Let's see what happens there. So notice how when I called initialize, it emptied the stack, and now when I'm calling top, I'm getting that the empty stack is showing. So that's why I'm getting that negative 99999. So that's showing that it's empty. Okay, let's take that away. Let's try let's stick to just showing the top. And then let's go ahead and try our copy constructor So second stack passing in the first stack, and then let's go see out second stack dot top and L, run that. We should see 45 twice, which we do. So our copy constructor is working fine. And is there anything else? Any other function we need to test? Initialize stack is full. Is all being used? All right, that's basically it. I mean, this is actually surprising. I didn't think it's gonna be this short. Only it's like 35 minutes. This is really basic, actually. I mean, we could make this more advanced maybe in another video. But yeah, basically we create a stack, we added members, we viewed the top of it, we pop things off the stack, we can push things onto the stack. Yeah, let's try doing that. So we have our top. Let's first stack dot pop. So now we popped off the 45, and then let's go ahead and push on another. Let's push on the value 1,000, and then view the top again. So we should see 1,000, and 45 will be gone. So if I do this, we get that 45 1,000. Let's pop and then let's repeat this process. Let's pop it and then print it again. Oops. So essentially, this will show 45. We take the 45 off. We push the 1,000. This shows the 1,000. We pop the 1,000 off. This will show what? What does this show? Question mark. I'm gonna guess and say 35. Let's see. Yep, and it does. So 45, 1,000, 35. The reason is because we popped the 45 off, we added the 1,000, we popped that off, and then we get the 35. So this is how a stack works. It's last in, first out. So the last one in was, let's see, where this push 1,000 is the last one in. So that's the first one out. When I call pop, that 1,000 is the first value to come out. The last one in, first one out. That's basically it. So yeah, that's it for this video. This is the basic stack. If you guys want to see a more advanced one, let me know in the comments, and I could do a more advanced one. Maybe we could do some resizing to make it maybe more realistic. But the next one we're gonna do, the next video is gonna be on a linked implementation of a stack, and then we'll do Q. But yeah, that's it for this video. If you have any questions, if I did anything wrong, which I could have, I make mistakes, I'm human, just let me know. So thanks for watching.